Okay, welcome back, everybody. Yesterday, last lecture, we ended with a couple of diagrams showcasing Markov chains for these situations that we found ourselves in. Just to quickly remind you of what we were doing, um, we had the following example where we had three states, 1, 2, and 3. This diagram indicates the proportion of people moving at each step, or the percentage of moving from one state to another. This transition matrix indicates that in the zero entries here, right, indicate that, for instance, I cannot make it from state 2 to state 1 in one iteration. Similarly, I can't make it from state 1 to 2 in one iteration. So these two entries are 0 as a result of that. And so, unlike the first example we had, actually the first two examples we had of this, we can't immediately say that t is regular based on this. Now, you might be able to say, or to ask the question, can I get from any state to any other state if I allow two iterations? And the answer, of course, is yes, as we see from this diagram. So, for instance, can I get from 1 to 2 if I allow two iterations? I could go from 1 to 3 or 3 to 2. That's fine. Could I go from 2 to 1 in two iterations? I could go from 2 to 3 and 3 to 1. Yes. Okay. So, this is nice. You could ask the same question about any particular state, and the answer is going to be yes, which tells you already that t squared. So before I even write it out, even though, obviously I can use MATLAB to compute t squared immediately if I want to, or I could, this is a 3 by 3, I could compute it by hand. It's not that big of a deal. Um, I know that t squared is not going to have any zero entries, right? Because I know this characterization of t squared as having entries telling me uh, the proportion of, ways, or the proportion uh, of, or maybe I should just say, the probability of moving from a state to another given state in two iterations, right? Or the proportion of the population that moves from given state to other given state in two iterations. Those are the entries of t squared. So note, I already know that t squared has no zero entries before I even write it out. Okay. Just from this analysis that we did. So for instance, if I do write it out, what is t squared here? So it turns out that t squared is the following. So I'm going to read row-wise. So this is 0.825, 0.003, 0.255, 0.005, 0.9614, 0.089, 0.17, 0.0356, and 0.656. Now you might notice, for instance, that these entries that were previously 0 and t they're not 0, but they are small, right? You might call them close to 0. The question is, does that make sense, right? Well, think about what has to happen here, right? This is t, this entry is t squared, and it's the 1, 2 entry of t squared. So that is 0.003. And this should be the proportion of people that move from state 2 to state 1 in two iterations. So if I'm moving from state 2 to state 1, I can't stay in state 2 because there's no way to get from state 2 to state 1 in a single iteration. So my first step, I have to move. There's only one other state to move to, so state 3. So that's a 2% chance of happening. And then I have to move from state 3 to state 1, right? And there's a 15% chance of that happening. And so the reason this is small is the resulting probabilities, right? The resulting proportions are small here, right? So this makes sense. Okay. Now you could cook this in such a way that these aren't quite as small, so they would go from 0 to something not quite so close to 0, but that's how this situation works. Notice that t squared 21 is 0.005, and just to reinforce this, this is the proportion of the population that moves from state 1 to state 2 in 2 iterations. So for the same reasoning, I can't stay in state 1 at the first step, at the first iteration, because then there's no way from getting from 1 to 2 in a single step, so I've got to move. So there's a 10% chance of me moving, and then from 3 to 2, there's a 5% chance of that thing happening. And so this is what I get as a result. Okay. So this is just checking that all of that makes sense. Okay. Now, of course, note that because this has no 0 entries, which we knew before we even wrote this down, but now that we have written it down, it has no 0 entries. This means that t is regular. So that our theorem applies. This has lambda equals 1 as an eigenvalue, and we can say all those things that we want to say about it. Okay. Now, like I said, I've already explained why these entries are the way they are. Let's see. Let me just write out, say, t to the 5th. Again, use MATLAB to compute this t to the 5th if you like. So reading row-wise is 0.6894, 0.02171, 0.4117. Next row, 0.03618, then 0.9118, then 0.1662, then 0.2744, 0.06646, and 0.4222. Now, the reason I write all these out is because I want to ask the same sort of questions about this t to the 5 here. So for instance, what does this entry in t to the 5 mean? So the 3,1 entry in t to the 5 is 0.2744. What does that mean? That means that in exactly 5 iterations, this proportion, this percentage of the population will have moved from state 1 to state 3. Okay, and you can think about the ways that you could have done that, right? So exactly 5 is the only restriction here, so there's a lot of things that you could have done to move from state 1 to state 3 in exactly 5 iterations, right? In fact, you could have stayed in state 1 for the first 4 and then moved to state 3 at the end. That's one possibility, right? Okay, you could have moved from state 1 to 3 to 2, back to 3, and then stayed in 3. That would also work, okay? So this this characterization we have of the entries of powers of t is very powerful, and this allows us to know exactly what is meant by each of these entries in this matrix. Okay, let's have a look at the other example. So we had an example that looked like this, and we noticed that in this example, t is not regular. And the way that we noticed this was because you were always going to have a zero entry in any power of t, because there are states that are unreachable. So if you begin in states 4 or 5, you can never reach states 1, 2, or 3. If you move to states 4 or 5, so via this connection here, right, you can't get back. All right, and so t to the k is always going to have at least one zero entry, which means by definition it is not regular. So t is not regular. So what this means is that our theorem doesn't apply as stated. It might not have lambda equals 1 as an eigenvalue, and so we can't use the theorem to crank out this steady state vector. Okay. So note while I can't get from state 1 to state 5 in one iteration, I can in 4. So the 5-1 entry in t is 0, but the 5-1 entry in t to the 4th is not 0. Now, this is exactly the same type of thing that happened in our previous example, right? So in our previous example, in t, we had these 0 entries. Those corresponding entries in t squared were not 0 for the obvious reason that I can't get from 1 to 2 or from 2 to 1 in one iteration, but I can get from 1 to 2 and from 2 to 1 in exactly 2 iterations, right? So, so in this case, the 5-1 entry in t is 0, but the 5-1 entry in t to the 4th is not. Okay, you can actually compute what this is. In fact, let's see. In 4, how many choices do we have? In 4, we kind of only have one way of doing this, right? So I can't go from 1 to 2, so I have to go from 1 to 3. And then I go from 3 to 2. I'm not allowed to stay here. It would take me too long. So I go from 3 to 2. And then if I'm doing this in 4 iterations, I have to move it pretty fast. So I got to go immediately from 2 to 4 and then from 4 to 5. That's the shortest possible way I could do it. So actually, I know in this case, because there's only one of these, I know what the 5-1 entry has to be, and it's just 0.10 times 0.05 times 0.01 times 0.30. That's what it has to be. So it's got to be 0.000015. Okay. So this using a similar way of thinking, I can also try to compute some entries in the same way, where I'm doing this for less power so that maybe I have more choice. So I'll do that here in just a second. Let's see, I had a question in chat. The midterm will be next week. And you'll have 24 hours to do it. So it will it will take place next week, toward the end of next week. So I'll let you know via Elm's announcement when that will be. Okay. So next, What about we have the situation where we are trying to compute the 3-1 entry in t cubed. So note, we can compute the 3-1 entry in t cubed as follows. I need to essentially enumerate the ways in which I can travel from state 1 to 3 in 3 iterations, right? So I'm traveling from state 1 to state 3 in 3 iterations. So how many ways can I do that? I could go from 1 to 3, then from 3 to 1, then from 1 to 3. That's 3 iterations, and that's still from state 1 to state 3, right? There's nothing about this that says it doesn't count somehow if all that matters is that I begin in state 1, end in state 3 in 3 iterations. So I could go from 1 to 3 to 1 to 3. That does it. Right? I'm counting the number of arrows here. What else could I do? I could go from 1 to 3, from 3 to 2, and then from 2 back to 3. That's also 3 iterations. So 1 to 3 to 2 to 3. And that takes me from 1 to 3 in 3 iterations. What else could I do? I could do the thing I mentioned in the previous example, which is going from 1 to 3 and then staying at 3 for the remaining iterations. So 1 to 3, and then to 3, and then to 3. That is fine. I could stay at 1 for the first 3 iterations, then go to 3 at the last step. So 1 to 1 to 1 to 3. And then I could do a mixture of these two, right? And this is kind of the last thing I can do. I could stay at 1 and then go to 3 and then stay at 3. So 1 to 1 to 3 to 3. And that is it. Those are the only 5. So you can check that this is, in fact, all you can do. All right, those are the only possibilities. Okay, so then how do I compute this entry here? Maybe I'll write it here. So this is the 3-1 entry of t cubed. So I am looking to have 5 terms in a sum that correspond to each of these probabilities, right? Or proportions, as we've been calling them. So 1 to 3, that's 0.10. And then back to 1 is 0.15. And then back to 3 is 0.10. So this would be 0.10 times 0.15 times 0.10. That would be for this term. Now we add to that for the next one, 1 to 3 to 2 to 3, right? So 1 to 3 again is 0.10. From 3 to 2 is 0.05. And then from 2 to 3 is 0.02. Okay, for the next one, so that takes care of this state. For the next one, 1 to 3 to 3 to 3, this would be 1 to 3 is 0.10. And then I remain at 3 the rest of the time, so this is 0.80 and 0.80. Next I have, so that takes care of this entry. 1 to 1 to 1 to 3. 1 to 1 is 0.90. 1 to 1 is 0.90. And then 1 to 3 is 0.10. and then one more, which is 1 to 1 to 3 to 3. So this would be 1 to 1 is 0.90, 1 to 3 is 0.10, and 3 to 3 is 0.80. And this sum of terms like this is exactly what gives me this entry, this 3-1 entry of t cubed. Okay, which, if you compute this, ends up being 0.2186. Now, the way, of course, of thinking about this, like what is this telling you? It's telling you that like roughly 22% of the population moves in this way from state 1 to state 3 in 3 iterations, exactly 3 iterations. Okay. Now, if we take our time for this problem, right, there are 5 states, so this is the transition matrix T is going to be a 5 by 5 matrix. If we actually write out the matrix, it would look like this. So for this example, our 5 by 5 matrix, notice it's going to have a lot of zeros, and it's going to have a lot of zeros because it is impossible to reach many states from many other states in a single step, right? So for instance, 4 and 5 can reach each other in single steps, but they can't reach any of the others, period, ever, in any number of steps, especially not in one step. 1 cannot reach 2 in one step. 1 obviously cannot reach 4 or 5 in one step. 3 can't reach 4 or 5 in one step. 2 cannot reach 1, 4, or 5 in one step. So this matrix T is going to have a lot of zeros in it. Okay, and if we fill this out based on these numbers, I'll put these numbers back for a second, then I'm going to read out the entries in the matrix, and you can go back and look and see that these actually match. So reading row-wise, the entries are 0.9, 0, 0.15, 0, 0, then 0, 0.97, 0.05, 0, 0. The next row, 0.1, 0.02, 0.8, 0, 0. Next row, 0, 0.01, 0, 0.7, 0.25. Last row, 0, 0, 0, 0.3, and 0.75. So notice what has sort of happened here in terms of from the transition matrix, you can essentially see which parts of your diagram are blocked off, right? Like, I'm going to draw this ever so slightly, a very slight line. You can see here that 4 and 5 are essentially blocked off with their only connection happening via state 2, right? So this is like intuitively how you can look at this transition matrix and see the diagram, essentially, right? Now, the benefit of the transition matrix, of course, is that it's a matrix, so you can do matrix computation things to it, right? Which is the benefit of the matrix over the diagram, right? The diagram might be better for kind of like intuitive understanding, even maybe problem statement, coming up with the problem, coming up with the situation you're in. But once you have the ability to write down the transition matrix, then you have everything you need in order to compute with that thing. And so, actually, we find that for, we'll say, very large K, T to the K times some initial vector x naught, and it doesn't matter here, any x naught, is actually the following. It's the vector 0, 0, 0, 0.4555, and 0.545. Okay. Maybe I'll leave off this 5. I could be more, could be more precise there, but I'll leave it at 3 decimal places. Okay, and so this suggests, right, and what I mean by doing this for very large K is just take this matrix T and use MATLAB to find like T to the 100, right? T to the 1000. Can you do that? Using computational aid for large K, we get this. And what this seems to suggest, right? This seems to suggest that T does in fact have a steady state vector for this. For this Markov chain, or for T, if you want to call it for T. Now, remember, right, the theorem and having regularity of T was nice because it guaranteed the steady state vector. When we cannot apply the theorem, for instance, in this case, in this example, because T is not regular, it doesn't mean that we definitely don't have a steady state vector. We might not, okay? It's possible that we don't, but we still might. So that's why I said there's no guarantees. With the theorem, there's a guarantee that you have a steady state vector. If you cannot apply the theorem because T is not regular, then there is no guarantee that you have a steady state vector, but you might. So this is an example of that case where we do. What would this correspond to, right? Just thinking intuitively for a second, what does this correspond to? What does this vector suggest? This vector suggests that everything eventually settles where? In states 4 or 5, right? This is suggesting that everything is eventually settling in states 4 and 5. But look, does that make sense? You might get caught up on the fact that this is a small probability event here, right? Because this is a 1% thing. Okay, so you might get caught up on the fact that this is a small probability event. But notice that eventually, right, if this is allowed to iterate forever, right, or indefinitely, what would happen? All the population here would eventually move here and never come back. So the big thing is because there is no way to get from states 4 and 5 back to states 1, 2, and 3, anything that moves to state 4 via this connection from states 1, 2, or 3 is there forever, right? It can never leave. It can never go back. So once you move over here to this part of the diagram, you're there forever, and you can never come back. And so whatever your initial distribution of population is, anyone that leaves via this route is stuck here in this part of the diagram forever. So eventually, everything would migrate to this part of the diagram and be stuck there forever. So it makes sense that they would settle here. And so what is actually going on is that in this diagram, these are like two distinct Markov chains that are like tied together by this one connection that it doesn't allow you to pass back and forth between them. And so this is almost acting like its own Markov chain separated here, which we could not only see in the diagram, but also we could basically see what's going on from the matrix itself. Okay. So intuitively, this does actually make sense in terms of how this behaves, how this functions. Okay. All right. And so let's do one more example here that I've already mentioned as kind of an example of showing non-regularity and some things that we get. So, picked up the wrong pen. So here's an example. So let's say that we have states 1 and 2. And each year, 100% of the population of each state moves to the other state. This is like a perpetually grass is greener civilization, or like star-bellied Sneetches of Dr. Seuss or something, right? So, so this is the deal. We already wrote down the transition matrix for this, which is exactly this one. Okay. Now, here's the thing. For this matrix, t squared is the identity, which means that t cubed is t times t squared, which is t times the identity, which is t. But then t to the fourth is the identity, and so on. Notice that this flipping back and forth between the identity and t itself tells me what? Tells me that every power of t always has a zero entry. i.e. t is not regular. So I gave this as an example earlier, not today, but yesterday, so in yesterday's lecture. And I mentioned that it's not regular in that example, but I didn't explain myself further, so now let's talk about this a little bit more. Okay, so notice that this seemingly has no steady state vector in the sense that every population flips year by year. So note, any initial population flips year after year, right? So, for instance, if we began with a distribution that looked like this, this would move to this, which would then move back to this, which would then move back to this, and so on. That's like the opposite behavior of settling, right? This is telling you that this limit for this initial vector just doesn't exist. Now notice, we can have a steady state vector, which is not really one, because it depends on the choice of the data, or of the initial data, right? If the initial data is exactly this, right? So this is technically a steady state vector in that if the initial data starts here, then it will stay here, but no other initial state vector will converge to it. Right, so if you choose any other initial state other than this, it is not, in fact, a steady state vector. Okay, so so basically, in this case, we effectively don't have a steady state vector in the sense that we had in the other examples, right? Even in the non-regular case that we just did for that 5x5 matrix, we ended up getting a steady state vector even though the matrix wasn't regular, right? And steady state in the true sense that you choose any vector and you get the convergence that we got, in the theorem statement. So we're very happy with that. But here's an example showing that when t is not regular, this sort of thing can happen. Okay. So that's all for the basic Markov chain stuff. Now, what do I want to say? I've said all this stuff kind of implicitly saying that everything I've been doing has been involved with Markov chains. I even called one of these things a Markov chain at least once, but I didn't actually define what a Markov chain is. So rather than give like a complete or try to give like a probability theory definition for Markov chain or whatever, I'm going to give a more vague definition, and you'll see why it applies to these things that we're talking about. So we will say, what is a Markov chain? So what is a Markov chain? And the answer is it is a stochastic or random or probabilistic process describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. So you could say that this is, you might say that this involves conditional probabilities, where the condition only involves the previous event. This isn't a probability theory course. You take stat 410. Oftentimes the instructor will get into Markov chains maybe toward the end of the semester. But the idea is essentially that we have a process, and it is not necessary for us to track everything that happens in the process. We only need to know what happened at the last step, at any step, and we can make all future claims we want about it. Now, why are these things that we've been drawing Markov chains, right? Because notice that at each step, the events that we're talking about, so moving from state 2 to state 4, all I need to know is that I'm in state 2 when I'm ready to move. So at the time step in question, if I'm in state 2, I'm treated the same regardless of if I have been there the whole time or if I just moved into state 2, right? So the only thing that matters is that I have attained state 2, and all of these probabilities, all of this thing is accurate. So you might hear people call that a memoryless property, but a lot of times when you talk about memoryless, you're talking about a specific thing to do with random variables, which is sort of related, but not exactly. So I won't say that. I'll just say that this is what I'm going to say about Markov chains. And you might have guessed, right, just based, especially from the vagueness of this, that this is going to describe a lot of events, especially things that might be amenable to computation. And you would be correct. So the examples are the kind of vague descriptions of population distribution and states. Of course, you can view, those states and those population distributions, you could just view those as probabilities of moving between the states, where the states are, not geographical states, as I said, but like states of being, right? Okay, so I'm going to talk about one application of Markov chains, kind of that immediately pops out. That's a nice and quick application of this stuff, which is Google PageRank. So note, this is named after Larry Page. This is not, that's kind of a funny, coincidence that you might think that PageRank comes from, the idea of ranking web pages, but it's actually named after Larry Page. So that's, just a fortuitous coincidence that his last name is Page. So anyway, Google PageRank, what is the idea? A ranking of web pages that is based on some sort of criteria, right? So now, what might you come up with when it comes to ranking a page? So you might say, well, idea, right? Look at how many pages link to that page. That might seem like a pretty good way of doing it, right? So page in question is linked to by 50,000 other pages. Wow, that seems like a great page and should rank higher than the page that is linked to by only 10 other pages. But right, but the 50,000 pages in question may be low quality or lowly ranked pages on their own, while in the other example, the 10 web pages that link to the other website that I was talking about may be themselves very highly ranked web pages. Now, you notice that there's kind of a self-referential problem here where I'm talking about a ranking of the pages while I'm trying to define the ranking of the pages, right? So, but then we immediately ask, how important, i.e. highly ranked, are those web pages, i.e. the ones that are linking to the page in question? Okay, and so we have this problem, right, that keeps going back and forth, which is I want to determine a ranking, but I'm going to base my ranking on the ranking of other pages linking to the page in question. So this is a little tricky. How might I actually do this? So let's come up with a diagram. Let us draw a diagram of this situation. Okay. So let's say in our example, just for the sake of it, let's say that the entire internet consists of 4 pages, right? So there it is. It's those 4 pages, P1, P2, P3, and P4. I'm going to draw a diagram that indicates the relationships these have, where arrows between them indicate a page linking to a page. So page 1 links to pages 2 and 3. Page 2 links to page 3. Page 4 links to page 3. But also page 3 links to page 4. Okay, so the arrows indicate links from a page to another page. Now, notice that at least, intuitively you might say this looks like a Markov chain, what we were doing with Markov chains previously, and it definitely does. You might also notice that this is, more generally kind of the underlying thing that's going on here. You might say is like this is a graph, right? If you know anything about graph theory, that you might say this is a graph or a digraph or something like that. But considering we just did Markov chains, you could even imagine that if we start assigning percentages, right? Note, if we start assigning probabilities here, this seems to be a Markov chain, or to describe a Markov chain, or to be described by a Markov chain. Okay. If we did that, right? And how would I do this, first of all, in a way? You might say, like, the simplest thing I could do is say, okay, page one has two outbound links, so I would assign them equal probability. So we'll say each of them has probability 1/2, right, or 50%. Here, there's only one link, so that has probability 1. Here, there's only one link, that has probability 1, that has probability 1. So this would be a very simple thing, but this is how I could handle it, right? But if I did this, if I assigned probabilities in this way, if this thing had a steady state vector, what would it correspond to? So here, the steady state vector would correspond to where a random web surfer would end up in the long term, right? And random web surfer, I'll call that RW, would end up in the long term. So it would describe a page, or maybe a block of pages, right? Think back to the example we did with 5 nodes in the previously, where 4 and 5 were separated from 1, 2, and 3. It would maybe describe like a block of web pages where eventually the random web surfer settles, right? So maybe this is describing like the block of the 10 most popular websites where almost everyone eventually settles or finds their way to, right? That's what the steady state vector would describe here. Okay, if we did this. Now, here's the thing, right? The thing is that the way that this would actually work is that a web page may not have any outbound links, right? So you might have a web page that does not link outwardly to anything. And the problem with that, think back again to like a situation like this, right? These 4 and 5 have some outbound links, but not to these other states, right? But imagine one of these. Imagine a 6th web page described here that has no outbound links. You can only go to 6, but you can never get anywhere else from 6. Well, there do, in fact, exist websites like that, right? There's websites that don't have any outbound links. So then how did you ever escape that website? Well, of course, the answer is that a random web surfer doesn't behave exactly like this Markov chain business where you are stuck, you are a slave to these probabilities and you're just going along this path, right, in these various states, and that's it. This is not really how people surf the internet. This is not how people traverse the internet, so that once you get to a website that has no outbound links, you are not stuck there forever. Thankfully, you can't actually leave. You can't actually just go to a random site of cat videos or whatever it is you want, right? So that's the idea. And so, what do I do to deal with that, right? So how can I make this situation model the behavior of a random web surfer more accurately? So This is where the Google PageRank algorithm comes in. So maybe I'll describe it on the next page so I have full room to talk about this. Google PageRank algorithm. Maybe I'll call this GP for whenever I am referring to it. What is the idea? So assume a random web surfer starts at some page. Secondly, if the page has outbound links, then there's an 85% chance that the random web surfer chooses one of those links. Okay, and those links are equally likely. There is a 15% chance that the random web surfer chooses a page at random from all possible pages. Okay. Now, how to deal with pages with no outbound links? How do you escape a page with no outbound links? Well, how do you escape it in real life, right? When you visit a site on the internet that has no outbound links, what do you do? Like, is that it? Is that your home page now, and you're never again going to any other site? No, of course not, right? You are picking your random favorite cat video site, right? That's what you're doing. So this is if the page has no outbound links. Okay, then there is a 100% chance that the random web surfer chooses a page at random from all possible pages. Okay. And the assumption is that the random web surfer will continue to do this forever. Okay. Now, how does this work? You might say, once you realize what it is that's going on here, you say, okay, this is definitely a Markov chain. Yep. Okay. But you might also say, well, the thing I drew before doesn't really accurately depict what it is that's going on here. And the reason why is in order to incorporate this business about this 15% chance of randomly choosing a page, I would have to connect every page to every other page with that blanket chance. I'm not going to do that in any of the diagrams because it would be too annoying to do that. And so you're just going to basically say this is floating in the background in all of these diagrams, right? So we don't actually have to connect all these things. So now let's go back to this example. Based on this, let's go back to this example that we had and actually say what it is that is going on. So first of all, we note a few things in this example. So there is a weight connecting all of these things. So one, I'm not going to draw it here, but there is a weight of 0.15 divided by 4. So that's my 15% chance divided by 4. There's 4 total pages here. Connecting P sub I to P sub j for all I and j. Okay. There is also an additional weight. Maybe I'll put it over here. An additional weight of 0.85 times 1 over n, connecting P sub I to P sub j, provided that P sub I links to P sub j and that P sub I links to n pages total. So where does this come from? This is the equal weighting to all outbound links, right? So my underlying PageRank algorithm says that there's an 85% chance a random web surfer chooses one of those links, and those links are equally likely. So if there's n of them, right, each n of those are equally likely, so that accounts for this additional weight. 85% chance, equally likely, 1 over n. Okay, so that is where that is coming from. Okay. Now, this means that I can actually, using these weights on this picture, along with these weights that are connecting everything to everything else that accounts for my randomness here, I can actually write out the transition matrix T as follows. So there's my weight for my random page jumping, which is random amongst all pages. And so the matrix here is simply a 4x4 matrix of nothing but ones. That's for that slot. And then added to that is 0.85 times I have now written my transition matrix here, and I've scaled all of them according to how these need to be scaled based on outbound links. So for instance, here, right, I don't go from anywhere to page 1, so my first row is all zeros. Okay, from page 2, I can get there from page 1, but page 1 has 2 outbound links. So each of those outbound links has to be weighted 1/2. This is 1/2. The rest are 0. That's the only way to get to page 2 is from page 1, and it's one of 2 links, so 1/2. Okay. Here, page 3. Well, I can get from page 3, I can get to page 3 from either 1 or 2. Okay. In the case of 1, there are 2 outbound links, so that's again 1/2. In the case of 2, there's only 1 outbound link, so that's a 100% chance of happening there. And the rest of these are 0, because I can't stay on page 3 as part of this. and I can't go from anywhere else. Oh no, wait a minute. No, these aren't. This one isn't 0. I can in fact get to page 3 from page 4, so this is a 1. Sorry, I don't know if it was because it was close to these P's or what, but I didn't see this arrow for a second. It was also slightly off the screen, so corresponds to my vision. Here, this last one, I can only get to page 4 from page 3, and there's only one link, so there's going to be a 1 here and zeros everywhere else. And so that is my matrix. Now I have to multiply these and then add these all together. So let's do that. All right. So then what T do I get if I do that? The T I get reading row-wise here is 0.0375, 0.0375. I have the same entry in all of these. Why did I write that there? So same entry along the top. Second row is 0.4625, 0.0375, 0.0375, 0.0375, then 0.4625, 0.8875, 0.0375, 0.8875, and lastly I get 0.0375, 0.0375, 0.8875, and 0.0375. So this is what I get for my matrix T. You can check for yourself that this is in fact a transition matrix. All of these columns sum to 1. Okay, notice that this is regular. In fact, not only is it regular, but I can actually see that, hey, from this process, the way that this works, I'm always going to have this thing weighted in this way, which guarantees that all these entries are non-zero. So I'm always going to get that this thing is regular, which means by the theorem, T has eigenvalue lambda equals 1. Notice that obviously, it has more eigenvalues than that. Counting with multiplicity, right? It's a 4x4 matrix. So it's got 4 eigenvalues, but we don't care about that because we only care about the lambda equals 1 eigenvalue because that's the one that the steady state vector corresponds to, right? So that is the deal. Now, what is our corresponding steady state vector? Is called our ranking vector. What is that? So in this case, our ranking vector, the corresponding steady state vector is 0.0375, 0.0534, 0.4711, and 0.4379. And so what this says is that P1 has PageRank 0.0375, and so on for P sub 2, P sub 3, and P sub 4. So here, this vector contains the page ranks of pages 1, 2, 3, and 4. Okay. Does this make sense given the diagram? So let's Let's bring our diagram back. Okay, so here's my diagram here. Does this make sense for a ranking? So, why is page 3 important? Because a lot of pages relatively link to it, right? So page 3 having the highest page rank among them, it's linked to by the most pages. Now, what about page 4? Page 4 has the second highest page rank, but it only has a single page linking to it, right? P2 also has a single page linking to it. But the single page linking to P4 is an important page because it's linked to by a bunch of other pages. So P sub 4 has a higher page rank than P sub 2 because the only site linking to P sub 2 is P sub 1, which has no sites linking to it. So it is the least ranked, right? In fact, even though P sub 2 has one page linking to it and P sub 1 has none, it's only slightly more important, is according to the ranking, than P sub 1 because P sub 1 is so meaningless, right? A link from P sub 1 doesn't mean anything because P sub 1 is not very important. Okay? All right. And so you see how this goes, right? In fact, you can see even how to generalize this immediately. So how to generalize, let's just very quickly say like, right, the general PageRank matrix looks like the following. So for an internet with n pages, you have T is 0.15 over n times, this is some n by n matrix of ones, plus 0.85 times a matrix containing vectors, we'll call them v1, v2, out to vn, okay, where the vectors vi are given by the following. So 1, if page I has k outbound links, then the jth entry of the vector v sub I is 1 over k if page I has an outbound link to page j, and is 0 otherwise. So it's 0 if there is no outbound link from page I to page j. And then if page I has no outbound links, then every entry of v sub I equals 1 over n. Then every entry of v sub I is equal to 1 over n. This is including the part in the Google PageRank algorithm that says if the page has no outbound links, and there's a 100% chance that the random web surfer chooses a page at random from all possible pages. There are n possible pages. Okay, so that is where that entry comes from. Note, no matter the size, right, we still only care about the lambda equals 1 eigenvalue, which means we don't need to find eigenvalues for this matrix. Once we know, right, that T is regular, the theorem tells us that it has lambda equals 1 eigenvalue. So then we just need to find the corresponding eigenvector for it and make sure that it's a probability vector. So we have to scale it, by 1 over the sum of its entries, potentially. This gives us our steady state vector, which we're calling our ranking vector in this context. Okay, and so what this means is that instead of having to find an eigenvalue, which involves, finding the roots of an nth degree polynomial, all that's done for us. All I need to do here is find an eigenvector corresponding to that eigenvalue, lambda equals 1. But finding an eigenvector means solving a system of like homogeneous matrix equations, right? So that's the key, right? That's all I have to do. I have to solve in equations, right? So it's a system of in equations that I'm solving to find this eigenvector, and that is essentially all of the work that I have to do in order to do this. Okay. So that is it. That basically finishes up Google PageRank. So this gives us a nice application of this Markov chain stuff. We may talk about some other applications of Markov chains soon in the future, but I think this is a good enough stopping point for now. So I think I'm going to end lecture here, and we will begin a fresh topic on Monday. As I mentioned in the chat to a question, your midterm will take place next week, toward the end of the week. So don't worry about it yet. You've still got a little bit of time. In fact, who knows? Maybe it'll even be Monday of the following week. So maybe you've got even more time. But you're going to have homework 2 is going to be posted very soon. I'm also going to post an announcement on Elms, kind of going over some guidelines for the homework. I know I already mentioned some others. I'm gonna mention some more as well to make sure you're getting the most out of the homework. So be on the lookout for that. But anyway, I think I'm gonna stop here, and I will see you all tomorrow, or well, Monday rather. Next lecture, right? It doesn't matter. Maybe you're watching all these lecture videos at 10 times speed or something all at once. So I might see you in the next second or two. But anyway, I will see you later.